Alright, this is going to be a quick video tutorial about how I've been doing signal decoding on the captures that Damien has. So first things first, we'll go into Logic to load his captures. I'll go here to the power supply SPI1 cold start. I'll bring this full screen for a second to kind of show the details a little bit more clearly. You can right click on these, bring the vertical size of the signals up a bit. First thing I might want to do here is kind of scroll mouse wheel up here upward to see what we're looking at. You can see that he's already got the signals figured out. This is the enable signal. It's active low, so as soon as the signal goes low, we are listening for bytes. Clock signal here. Now, first thing I might want to do is click around or move around here a little bit. See that currently it's telling me it's about 2.4 megahertz. It says 2.66 there, 2.4. So I could say that the SPI is probably running at a speed of approximately 2.4 to 2.5 megahertz. That's not terribly important to figure out, but it might be useful, say, if you're going to try to make your own control board. You need to know what speed you can talk to this chip at. You can look here, see that it is right about 2.5 megahertz. So with that out of the way, zoom out a bit. Look up here and see the bytes being sent and received. MOSI means master out, slave in. So this would be the signal coming from the control board, and MISO is master in, slave out. So this is the signal coming back from the chip, in this case the power supply chip. So you can look here and see that currently they are the same. So what is sent is being received. I will go here to the datasheet, go to SPI interface, and this can be a little bit daunting at first to try to figure out. A lot of times they have kind of dense text in here. Doesn't really explain very well how things really work. A lot of times you have to kind of really think this over, go back to your signals and kind of go back and forth and see what it is they're actually talking about. One of the most key pieces right here is this diagram right here where it says SPI access timing. But really, if you look at this, you can see SDI is MISO, the master in, slave out, and SDO is the output. So what we're seeing here is you can look at this is 1 bit, 2 bits, 3 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you can see on their diagram there are 16 bits on the diagram. And if you look here at the signals that we're seeing, they do seem to be grouped in groups of 2 bytes, so that's 16 bits. Leave it this way that Damien has it, or because we're now guessing that it's 16 bits, you can come in here and say that there are 16 bits per transfer. And now here we have everything grouped into 16-bit transfers, so that might be a little bit easier. I had left it in 8-bit and just copied the 2 bytes over, but it kind of is just up to you. You can see also a reason to think that this is 16 bits per transaction is that the enable line goes low and then high in between. So the enable line is only low for 16 bits at a time and then goes back high again to notify the chip that we're done with that transaction and we're on to the next 16-bit transaction. So that's one of the keys to find out how many bytes, how many bits you're talking about for a command. The next thing here is that you can see of the 16 bits, the first bit here is set as a special function, and then the next 6 of them are another function called A, and the next 8 of them are D, and then there's P here. Now these are the address bytes. When you're sending commands to the chip, you have an address for which register on the chip you are attempting to access, either for reading or writing. So that will be sent in these 6 bits. If you're writing, you will send the 8-bit value that you want to write to that register as those bits. If you're reading, you'll just send zeros, and I can show you that in a moment. Parity is explained up here. The parity bit's set to 1 if the number of 1s in the output stream is odd. The parity is 0 if the number of bits in the output stream is even. So basically it's just ensuring that there's an even number of 1 bits. If you look at the bits here, there should be an even number of zeros and ones on each time the clock ticks. There should be an even number. One of the things that you'll be doing here to figure this out is you'll want to bring a calculator up. I'm using Linux, so kcalc works for me. You want to put your calculator into, say, programmer's mode, or it's called numerical system mode here. You can type in the numbers. They're in hexadecimal, so you want to make sure that you're selected there. 8756. So that's the first command. And we can look at that in binary and count here. 1, 2, 3, 4, 5, 6, 7, 8. So you see that there are 8 1 bits in this message, so you do not need a 1 in the parity here to make an even number. You're already set. If you had seen, say, 7 1 bits here, then the parity bit would be 1 to make it even. So that's an even parity scheme that they use here, just the 1 bit, to make sure that communications have not been corrupted. So what I would do here is, they say that these are 16-bit commands. So I would go in here with the binary, copy that. I'll start a different text file. And it shows up with 1B in front, that, or 0B in front. That just means that it's binary. I usually delete that. And so we had the first bit there, then 1, 2, 3, 4, 5, 6 bits is the address. 1, 2, 3, 4, 5, 6, 7, 8 is the data bit. And the last one is parity. The first bit, I don't know if I explained it before, this first bit up here is the command. If that's a 1, we are writing to a register. If that's a 0, we are reading. And you can kind of see that up here. It does explain things a bit. A read operation has to start with the command bit being 1, B0. This just means that it's 1 bit, and then B0, it's a 0 bit on that 1 bit. And a write operation has to start with command bit being a 1. So in here we can see that the command was a 1, so this is a write. The address bits are 1, 1, the lower bits. That's in binary. You count. This one's worth 1, 2, 4, 8, 16, and 32. So you just add those up. 1 and 2 is 3. So we can say here that this is a write to register 3 value. And the value will be this right here. So you can copy that and see that that value is AB. So the first command that we see here, 8756, is write into register 3 the value AB. So now in this SPI interface, they will show you register descriptions. So you can go down here and look for offset address and see that that register 3 is the protection register. So we go there, click on that, and go to where the protection register is. And it says this register is used to request write access to protected registers. To unlock it, you would write 4 consecutive bytes AB, EF, 56, and 12. Well, we just now decoded that this is a write to that protection register, and we can put that in here. Value AB, which was the first value that we should write to unlock. So then we can go back in. The next one is 87DE. So in hex, we'll do 87DE. Get the binary of it. Go over here. Remove that header. Break this back up. And that is a write still to register 3, which is the protection register. This time the value is these bits up here. What I usually do to cheat, because this is 1 higher, I just divide by 2 to slide everything back. So if you're in hex, you can divide by 2, and the value at those first 8 is EF. So looking back, EF is in fact the next byte that we were expecting to get for an unlock sequence. So far we are successfully decoding the unlock bytes. And in fact, you will find that if you keep doing this, 86AD and 8625, you do in fact end up with ABEF 5612 as the unlock key. So that's a quick overview of how I do the decoding. Basically, it's just a lot of grunt work going back and forth, reading the document to figure out how they set things up, looking at the graphic here to see how these 16 bits are used, and then just going here to the register descriptions, looking up the register that it says we're accessing, and then clicking on that to get a representation of how the register is laid out. Now, when you have a given byte sequence, let's say that we'll go back in here and say just EF to get the bottom one. Let's say that this register was set to EF, and you look in here, they've got this laid out the same way your calculator will show you. So a 1 here is bit 7, a 1 here is bit 6, the 1 here would be bit 5, the 0 here would be bit 4, and so on. So the layout's the exact same. You can look from your calculator to up here and figure out what that means. In this case, on this register, the top 3 aren't used, so you really wouldn't probably see something here. But the bottom 5 are all in 50 cycle increments, so you would look here and see that the bottom 5 bits are 1, 1, 1, 0, and all ones in the bottom here is 15, so it'd be 15 times 50 would be the value that you'd be looking for. And I can show that a bit more in the notes that I'd originally taken. Here is a whole sheet filled out with my notes as I went. I had anticipated that it was 2.4 megahertz. I wanted to remind myself that read operations have the high bit up there at 0, and write operations have the high bit as 1. I wrote down the unlock and lock codes just for future reference. And then I wrote down how the layout is. That's just this graphic right here. So the top bit is 15. They're numbered 0 to 15. So the top one is 15. That's where the reader write bit is. Then the address is the next 6. The data bytes or data bits for writing are the next 8. And the last one is the parity bit that tries to make sure that we have an even number of 1 bits across the whole thing. So here I did the decoding of the protection register to unlock it. Then what they did is actually read. So you can see how reads differ here. Bring this over so it lines up. When you do a read, the top bit is 0. Then you send the address that you want to read. In this case, that's 2 and 4, so register 6. When you're reading, you don't send any actual byte there, so just all zeros. The parity for this just happens to be 0, so what this decodes as is a read to the watchdog config 0. If you go here to the register descriptions, you'll see 6 is watchdog config 0. I'll kind of work out the example here because this is an actual sent value. So we'll go back here. There we have that we received these bits right here as a reply. So how I would have decoded that, I'll kind of shrink this up here so you can see it at the same time. 0 is when in this bit, but we see here that actually the top 4 are all mean one thing. So we would grab these top 4 here that I had written down, and that is 6. So the watchdog error threshold to generate a reset and enter the init state is 6. And we'll see here that I did write that down, watchdog error threshold 6. So the next one down is a single bit then. That's a 0. We look at that as 0 in WWDEN. Look that up here, and it says request window watchdog enable. So 0 means that it is disabled. And you can just keep doing that down the line. The next one's a 1. So down here, a 1 is request functional watchdog enable, and we are enabling that. And then the bottom 2 are zeros. So that means external watchdog input is used as a trigger, and 0.1 millisecond tick interval. So that kind of shows how you can go about laying out the bits that you're seeing. I'll actually show you that real quick too. That is right here. So you can see that we sent 0C00 and got back 80C8. So 0C00 and 80C8 are the value that we were decoding there. The sent and received byte are different because this is a read and the chip is actually sending a reply back, whereas normally if the chip is being commanded to write something to itself, it just reflects back all the traffic that you sent perfectly so that you can see that you did indeed send it properly. So that's a quick outline of how to do it. It is kind of a long process sometimes, but it's not terribly complicated, just time consuming, going through, grabbing the bytes here, copying them into a calculator, finding out what the bits are, pasting the bits into a spreadsheet or a document, and then breaking them up the way that the document told you that they set out the traffic.